So, we were talking of logic gates. I talked about NOT gate, and then I talked about AND gate, and AND gate I explained in terms of the switch and also then using diodes. And then I told that I can also do it with transistors. So, let me describe that. It is essentially the same idea, two switches in series and transistor can act as a switch. So, you can make a circuit, you take two transistors, this is NPN transistor, and then you connect it in series in this fashion. This is your ground, and these are the two input points, and here you have biasing, normal biasing you can do. So, you can put resistances, here also you can put resistances in the base circuit. These are the input points, typically say 10K here, 10K here, 4.7K here, like that. So, what happens if these A and B, which are the input points, remember for AND gate what I need is the truth table is 0 0 0 and then 0 1 is also 0, 1 0 is also 0, and only if both the inputs are high the output is high, that is the truth table. So, if A is 0, B is 0, you are not giving any biasing here, you are not giving any biasing here, you are connecting it to ground, you are also connecting it to ground. In that case, both the transistors are in cutoff mode and therefore no current goes. And if no current goes through this collector, then no current goes through this resistance, and then you know that the potential here is same as this potential. So, but I do not want that, I do not want that, 0 0 should give me a 0. Okay. So, here 0 0, if I take output from here, then this is 1, but I do not want that. That is also a gate, I'll talk about it just after this. But if I take the output from this point, if this is Y, then see what happens. If there is no current in the transistor anywhere, no current here and no current here as well, and if no current here, then this is 0 potential, this is also 0 potential. So, it is low and 0 0 becomes 0. What about A is 0, this is grounded, but then B is 1, here you are giving that high, so called high volt. So, this transistor is in conducting mode because of this biasing, but the current cannot go because the current will be blocked here, this is in cutoff mode, and ultimately the same story, no current goes through anywhere, and then you have the same 0 output here. Okay. Same thing is A is 1 and B is 0, and only if A and B both are given high voltage, then both are in conducting mode, saturation mode, and then you have current going, lot of current going from emitter, the current goes in this direction. So, if this is 0 potential, this will be at a higher potential, so that V is equal to R I is satisfied. So, 1 1 gives me 1. So, this is how we can do this AND circuit. And if I take the output from this point here, if I take the output from this point here, what will happen? Suppose this point I say is Y, then what happens? In that case, 0 0, let us see what happens at 0 0. I have already described, if this is 0, this is 0, both the transistors are in cutoff mode, no current here, no current here, and therefore this potential will appear here. So this will be high, so this will be 1. What if A is 0 and B is 1? Once again, if this is 0, this is in cutoff region, it does not conduct, although this can conduct, but after all the current needs the full path. So no current here. If no current here, no current here, then again this potential appears here, and therefore this is 1. So 0, 1 also gives me 1, and similarly 1, 0 will give me 1. And if both are 1, 1, A is 1, B is 1, A is high voltage, B is high voltage, then both the transistors are in saturation mode, both can conduct current, and therefore you do have a current. And once you have a current, you remember in collector the current direction is this, emitter current direction is this. So if the current is going like this, you have a voltage drop on this, and potential will decrease as you go through this, and in saturation mode this potential is very, very low, and therefore what you get is 1, 1 and 0. Now this is also a very useful, in fact very, very useful truth table and very, very useful configuration, and this particular kind of gate which gives me these outputs is known as NAND gate. So I have described you a NAND gate. This is the picture for a NAND gate. So this is for AND gate and this is for NAND gate. Not AND. It is opposite of AND. If this is 0, this is 1. If this is 0, this is 1. This is 0, this is 1. This is 1, this is 0. So it is just not of AND, and therefore the name NAND. The symbol for NAND gate and AND gate, for AND the symbol is, you write make a structure like D, and then you take two lines here and represent these as inputs. So this is A and this is B. So for symbol you don't write AB, okay, and then you put a line here and a dot here. So this is the input, or let me write, this is the input points and this is the output point. So that is the symbol for AND gate. And for NAND gate the symbol is, you again make that D, you again put two lines to show the input points A and B, and then you put a circle out here, and then you take a line, and this is the output point. So this is the symbol for NAND, and this is the symbol for AND. So this circle here denotes NOT. Remember the symbol for NOT? The symbol for NOT was like this, single input. It was like this. So this circle, wherever you see this circle, you understand that this is NOT gate. So AND and then NOT of AND, and that is the symbol for NAND, and this is how you can realize this NAND gate. Okay, now the next will be OR gate, OR. So our next is OR gate, and the OR gate means A, B, Y, and then if any of these two inputs is high, this should be high. Only if both the inputs are 0, this will be 0, otherwise it should be high. So that is called OR. 0, 0 should give me 0, but then 0, 1 should give me 1, and 1, 0 should give me 1, and 1, 1 should give me 1. So A or B, any one, at least one of these two, both is okay, is high, then the output is high. Only if both of them are 0, then it is 0. So, that is known as OR, and this is the truth table for OR. If you think of switches, it is like this. It is like this, and then you have any of these two is on. So, you have like this. Here is the power source, and then here is that lamp. Let us say this is that lamp. So, what will happen? If this switch S1 and this switch S2, if both are open, then the lamp is off. So, if both are 0, then output is 0. Any one of them you close, making high. So, this represents high. So, any of the switch that you close, this becomes 1, it is still 0, but then the current can go through this and lamp will be on and output will be 1. And if both the switches are closed, then also the output is 1. So, that is like a switch. With the transistors, you can take two transistors and connect them just in this configuration, parallel configuration. So, you can take two transistors, just take two transistors, and both the collectors you connect together. So, let me connect it this way. Both the collectors I have connected it like that, and both the emitters you connect it together. So, if I take it here, let me show it this way, and then this is connected. And then here are the input points. So, you can put resistors, and these are the input points A and B. And then the collectors, the common collectors, from here you have your biasing. And emitter here you have that emitter resistance, and it goes to 0, and this is the ground. So, this is the ground, right. So, if you want to make any of these two as 0, connect it to ground. If you want any of these two to become high, let us say 5 volts or 6 volts or 4 volts, then you connect that battery, and the negative of the battery will be connected to this. So, that is the meaning of this circuit. So, this is just just an implementation of this kind of circuit using transistor as a switch. Okay. So, you can work out what happens if this is 0, if this is 0, then what happens to output? From where do I take the output? If I take the output from here, what will happen? If normally we take output from here in amplifier configuration. So, if I take output from there, if this is 0, this is in cutoff mode. If this is 0, this is in cutoff mode. So, 0 0 is giving me high, and that is 1. I do not want that. I want 0 0 to be 0. So, once again I will take the output from here. This will be our Y. So, 0 0 will give me 0, no current. So, this is 0, this is 0 potential. So, 0 0 is 0. What happens if 1 is 0, other is 1? So, now if A is 0, but B is 1, this is grounded, this A is grounded, this A is connected to this ground line. But then B is connected to the positive of a battery and the negative is connected to the ground. So, that this is at a high voltage. Okay. High voltage means whatever my high, 4 volt, 5 volt, 6 volt. So, this is at high. So, this is now conducting, and if this is conducting, the current gets a path, the current gets a full path, circuit is complete, the circuit is complete, right. The current can come from emitter, the current can come like this, it can go like this, and then through this battery, collector current can go like this. This is not conducting, this is in cutoff region, but then the current can always come through this, and then it can come here, and from the base side the current. So, this whole operation is on. What about this? What about this? If there is a current If there is a current, then this potential is high and this with respect to this potential, and so you have high voltage here. So 0 1 will give you 1, and similarly 1 0 will give you 1, and 1 1 will also give you 1. If this is also conducting, this is also conducting, there will be a division of current. There will be a division of current. One current will go through this line, one current will go through this line. So that's fine, it's perfectly all right. So in both cases, you have a current here, you have a current here, and if you have a current here, the output here will be high. This is 0 and the current direction is this. So that is OR. What is the symbol for OR? The symbol for OR is like a, what is it, concavo-convex lens. Okay, it's a concavo-convex lens. So that's the kind of symbol, and you put two input lines. These are the input points, and then you take another line. This is the output point. So that is the symbol for OR. Now in the same circuit, if you take output not from here but from here, if this is Y, what happens? Just opposite of it. Whenever there is a current, this potential is high because there is a current, but since the current is this way, this potential is low. And if there is no current in this, then if there is no current, if 0 0 no current, then this potential is same as this potential, this is low. But if this is low, then you have no current here, so this potential appears here and that is high. So it is just opposite of this, it will be just not of this. If I take the output from here, then the truth table will be ABY. If I take it 0 0, here 0 0 was 0, here 0 0 will be 1. Then here 0 1 was 1, so here 0 1 will be 0. 1 0 was 1, so 1 0 will be 0. And 1 1 was 0, so 1 1 will be 1 1 was 1, so 1 1 will be 0. So wherever there was 1, it becomes 0. Wherever there was 0 in the output, that becomes 1. So it is not of this, and this is known as NOR gate, N-O-R, NOR gate. Okay. If you take the output from here, it becomes an OR gate. If you take output from here, it becomes a NOR gate. And what is the symbol? The symbol is, you make a OR symbol, and then you put a circle here to show that NOT operation, and then you have the output point. So that's the symbol. Okay, so these are some of the very basic gates. You have AND, you have OR, you have NOT, then you have NAND, and you have NOR. Now these two gates, NAND and NOR, they are known as universal gates. And why they are called universal gates? Because using only NAND gates, you can make any other gate. You can make AND, you can make NOT, you can make OR, and any combination you can make. So only using NAND gates, if you have sufficient number of NAND gates, by connecting 1, 2, 3, 4, 5, 6, 7, 10, whatever is the desired digital circuit, you can make only using NAND gate. And similarly, you can make any desired circuit, digital circuit, using only NOR gates in proper combination. So that is why they are called universal gate. So let me show how NAND gate can be used to form the three basic gates, NOT, AND, and OR. First, let us try to make this NOT gate. So everything using NAND gates, and pretty simple. NOT is you just take one input and one output, and this was the symbol, and what was the truth table? A is here, Y is here, 0 1 1 0, simple. And you take just a NAND gate, this is NAND, and then your input just one single input, but same input you connect to both the input ends. So this point is A and this point is finally Y. So what happens if A is 0? If A is 0, in the first input you are giving 0. In the second input also you are giving 0. So 0 0 AND operation, AND operation. 0 0 will give me an output of AND as 0. So you can think of this as AND and then this is NOT. So AND will give you an output 0, and then the NOT will convert that 0 to 1. So Y will become 1. So if this is 0, this is 1. And if A is 1, if this A is 1, you are giving 1 here, you are giving 1 here. So both the input are 1 1. AND gate 1 1 will become 1. So here it is 1, and then NOT of that will become 0. So this 1 becomes 0. So only using the NAND gate I can get this NOT gate. How do I get AND? How do I get AND gate? So AND gate, the truth table is A, B and Y, like that. So 0 0 should be 0, then 0 1 should be 0, 1 0 should be 0, and 1 1 should be 1. So this is how, this is what I need. This is what I need. So for this, 2 NAND gates are needed. Let's try this way. This is A, and this is B, and this is Y. Let's try what happens with this circuit. 0 0. This is 0, this is 0. AND will give me 0. NOT of this will give me 1. Wait. This is like this. So you need 2 inputs here. So start again. 0 0. 0 0 gives me 0 here, gives me 1 here. So 1 goes here, 1 goes here. 1 and 1 will give me 1. NOT of that will give me 0. So I get 0. So this is done. Now let us see this one. A is 0, B is 1. So A is 0 and B is 1. 0 and 1. AND gate will give me 0. And therefore NOT of that will be 1. And so here it goes 1, here it goes 1. And 1 and 1. AND will give me 1 and NOT of that will give me 0. So this is 0, that's fine. Same story, 1 0 will give me 0, 1 1. So if A is 1 and B is 1, so 1 here, 1 here. AND will give me 1, so 1 here. NOT of that will become 0, so 0 here. So 0 here and 0 here. And 0 0 AND will give me 0. And NOT of that will become 1. So 1 1 will become 1. Okay. So this is AND gate. This whole thing is AND gate. With 2 NAND gates you can make AND gate. And then OR. Let us see how do I get OR gate. For this I need 3 NAND gates. One is here, 1 is here, and 1 is here. The first input I am giving here, this is the first input A, and this is that second input B, and the output of this goes as one input here, and output of this goes as one input here. So let me make the truth table of this digital circuit and see whether it is OR or not. So let us make the truth table for this circuit. A is here, B is here, and Y is here. First, A and B are both 0. A is 0. So this input is 0. This input is 0. 0 and 0 and will give me 0. Not of that will give me 1. So here it is 1. And similarly, this is 0. So 0, 0 will give me 0. Not of that will give me 1. So 1 here and 1 here. This will give me 1, and not of that will give me 0. So this will become 0. Okay? So this becomes 0. This is our Y. Final Y is here. So 0 here, 0 here, and then I saw that it is 1 here, and then it becomes 0 here. Next, 0 and 1. A is 0. So this is 0. Fine. So if this is 0, this is 0, this is 0, and gives me 0. Not of 0 is 1. So this is 1. And from this side, B is 1. So this is 1. So this is 1 and this is 1. And of 1 and 1 is 1. Not of that is 0. So this is 0. And this 1 and this 0 and of 1 and 0 is 0. Remember. And A and the AND of 1 and 0 is 0. So here it is 0. And then not of that. Not of 0 is 1. So this becomes 1. Okay, and same story, if you give 1 here and 0 here, A becomes 1, B becomes 0, similarly this will be 1. And finally, if both are 1, if this is 1, then 1 here, 1 here, 1 here, 0 here, so this is 0. And then here it is 1, so this was 0, this will also be 0, and 0 and 0, 0 A and D 0 will be 0 here, and not of that will be 1 here, so it is 1. And you can see that this is OR. So this gives me OR circuit. So using only NAND gates, you can create any other gate and or NOT, and all digital circuits are combinations of these. So you can do that. So it is a universal gate. And same is the story with NOR. This is your exercise. This is your exercise to show how to make AND gate using only NOR gates, NOT gate using only NOR gates, and OR gate using only NOR gates.